Hi everyone. Welcome back to our course manufacturing process. Today we are going to discuss about metal casting processes. So permanent mold casting process, as we discussed before, permanent mold casting process uses a metal mold which can be reused. That means several products can be produced from the same mold in comparison with the expendable mold casting. In expendable mold casting, you can use only one time, and hence there is an economic disadvantage associated with expendable mold casting. That's why sometimes we go for permanent mold casting. In permanent mold casting, the mold is reused many times, so mass production industries or several products can be produced at the same time. In such kind of industries, we go for permanent mold casting. Today we are going to discuss about basic permanent mold casting, die casting, and centrifugal casting. In permanent mold casting, we use a metal mold constructed of two sections. One is a stationary section or fixed section, other section is movable. So with the help of a hydraulic cylinder, we can move the movable section, and then molds are normally for casting lower melting point alloys. Normally we use steel or cast iron as the mold. So these metals are steel or cast irons for lower melting point alloys. Molds used for casting steel must be made of refractory material due to very high pouring temperatures. Now what we do is we separate it, and then with the help of a hydraulic cylinder, the mold is first step. The mold, this is the mold, two halves, stationary and movable. They are preheated and coated. Then after preheating and coating with the refractory material, the core is attached. You can see here these stationary and movable mold halves are joined together with the help of hydraulic attachment, and then core is attached with the mold. Core is used for producing holes or hollow section. Then after that, molten metal is poured into the cavity or into the mold, and whenever it solidifies, we get a product. We separate it, we move the movable half backwards, and then we can separate the product from the system. This is called a permanent mold casting process. Now we can see what other processes are available. What are the advantages and limitations of permanent mold casting? Very good surface finishing, because if you compare sand casting process, the surface is normally rough, whereas in permanent mold casting, the surface has a very good surface finish and good dimensional control or accuracy also. The rapid cooling, because the metal surface will dissipate heat rapidly, hence results in a finer grain structure. Whenever the structure becomes fine, the strength of the casting also increases. These are the advantages of permanent mold casting. So the limitations are generally they are limited to lower melting points, such as melting point metals such as aluminium, magnesium, copper, etc. Only simple geometries can be made by permanent mold casting, because if it is complicated, then dividing them into two and moving the part and separating them becomes difficult. High most of the mold is another limitation. Where we can find permanent mold casting? Due to high mold cost, it is best suited for mass production, large quantities, production centers. They use such kind of casting techniques. Generally, automobile pistons, pump bodies, and aircraft parts can be made by such kind of casting processes. Now we have a die casting, which is very famous, and you can see common process in manufacturing. Kind of permanent mold casting in which molten metal is poured into a cavity, mold cavity, under pressure, under high pressure. Pressure is maintained even during solidification. Pressure is maintained. Then mold is opened, and then the part is removed. So mold in this casting process, the mold in this casting process, we term it as dies. They are called as dies, hence the name die casting. So generally, in high production rates like 500 parts per hour or not uncommon, we can produce even in 1 hour, 500 parts can be produced using die casting. This is the beauty of the process. Normally, we use zinc, tin, lead, and magnesium These are the metals used for casting or used for die casting. So we have two types, hot chamber die casting and cold chamber die casting. We are going to discuss them in detail now. In hot chamber die casting, the metal is the molten metal is produced in the hot chamber. You could see here there is a pot, and here there is a plunger, and there is a cylinder here. This is the plunger. Like it will act like a hydraulic system. You can see here this is a hot chamber, and these are the fixed die and movable die. Fixed die it cannot move, and movable die it can be separated. There are ejector pins and there is a cavity. So when fixed die and movable dies are connected together, we'll get a cavity. This cavity will have the same shape of the product to be produced. So here what we have is a plunger. So as the plunger moves downwards, the molten metal which is already inside the chamber will have a higher pressure and it will be pushed into the cavity. So then the cavity will be filled with a molten metal, and it will remain, the pressure will remain as it is. So what happens is, under high pressure, when it is pushed into pushed into the chamber, what happens? It becomes solid. So after some times, cooling takes place, solidification takes place, and it becomes solid. So then it can be separated from these two can be separated. You can move the die outwards and you can separate the part from the die between the dies, and then you will get a final finished product. This is called hot chamber die casting. So in hot chamber die casting, with the dies closed, the plunger withdrawn, and the molten metal flows into the chamber. With the dies closed and the plunger withdrawn, molten metal flows into the chamber, and then you can see here, as it pushes, the molten metal will be pushed under high pressure, and then it will enter into the chamber. It will be filled with molten metal, and after solidification or cooling, you can separate them and you can separate the part out of the chamber. This is about hot chamber die casting process. So molten metal is poured into the chamber from external container, and a piston injects molten metal under high pressure into die cavity. High production, but not usually as fast as hot chamber machines because of. Now we are going to talk about cold chamber die casting method. In cold chamber die casting method, the difference is the molten metal is poured from a separate chamber to the system. Here you can see we have a fixed die and a movable die, and the molten metal is poured not from the system. It is poured from an external melting chamber, and then as the piston moves towards the chamber, what happens is the molten metal will be injected into the cavity. Molten metal get injected into the cavity because of the movement of the ram. Whenever the ram moves, whenever the piston moves, the molten metal will be pushed and the molten metal will be injected into the cavity. The cavity will be filled by the molten metal. So this is the process in here. With die closed and ram withdrawn, molten metal is poured into the chamber, and then the ram forces the metal flow into the die, maintaining pressure during cooling and solidification. This is called this is termed as a cold chamber die casting process. Advantages of cold chamber die casting processes are economical for large production, good accuracy and finishing, thin sections are possible, rapid cooling definitely yield to small grain size and hence good strength. Disadvantages are generally they are limited to low melting point alloys or metals. Part geometry must allow removal from die. These are the disadvantages. Now we proceed to our next portion, which is centrifugal casting, a family of casting process in which the mold is rotated and use the help of centrifugal force to producing a casting. That is called a centrifugal casting. It's a high-speed casting process in which centrifugal force distribute the molten metal to outer regions of the die casting. Normally we produce pipes, tubes, etc. with the help of centrifugal casting. We are going to discuss two main centrifugal casting techniques in here. First is true centrifugal and second is semi-centrifugal. In a true centrifugal, molten metal is poured into the horizontal rotating mold. There is a mold here, you can see horizontal rotating mold, and molten metal is poured into it. The high speed rotation of the mold rotates, and the high speed rotation of the mold results in the centrifugal forces that causes the metal to take the shape of the mold cavity. So as the mold rotates at high speed, centrifugal force forces the metal outwards, and hence the molten metal will take the shape of the mold cavity, normally used for making tubes, pipes, bushings and rings. Outside shape of the casting can be round, octagonal, hexagonal, etc., but inside is normally round in shape. Examples of part made by these are already explained: pipes, bushings, rings, etc. So this is the arrangement of a true centrifugal casting. Here there are two rollers which rotates the mold. As the mold rotates at high speed, what happens? Molten metal inside it will be thrown with the help of centrifugal force and attached with the surface wall of the tube of the mold, and hence it will form the shape of the mold. Hence we can produce tubes, pipes, etc. This is called true centrifugal casting. What are the dynamics behind centrifugal casting? We know that centrifugal force is equal to F is equal to mv square by r. F is the force, m is the mass of molten metal, v is the velocity at which the molten metal is thrown, and r is the inside radius. Now the force of gravity in its W is equal to mg, that we know it, where W is the weight and g is the acceleration due to gravity. So we have a factor called G factor, which is a ratio of centrifugal force divided by F divided by weight. So F divided by weight, F is mv square by r and weight is mg. So when you calculate the ratio, you will get v square over rg. So velocity we can be expressed as 2 pi n by 60 times r, or 2 pi r n by 60. We get pi r n by 30 as a velocity. When we substitute instead of velocity here, the g factor is pi n over 30 the whole square times r divided by g. From here we can calculate the speed of rotation required to produce a diameter d, which is 30 by pi times square root of 2g gf divided by d. Here 2g is the acceleration due to gravity, gf is the already I explained to you about the g factor divided by d. D is the diameter or inside diameter of the mold to be produced. If G factor is too low in centrifugal casting, the liquid metal will not remain forced against the mold wall during the upper half of the circular path, but will remain inside the cavity, and slipping occurs between the molten metal and the molten wall. And on an empirical basis, values of G factor must be between 60 and 80 to appropriate for horizontal centrifugal casting. So one thing we need to understand is the minimum speed required for a centrifugal casting is 30 over pi times square root of 2g gf divided by d. G factor must be between 60 to 80. If it is very low, too low, then the metal will not remain forced against the mold wall. We will not get a casting, perfect casting. Now we have semi-centrifugal casting vertical type. Centrifugal force is used to produce solid casting rather than tubular parts in semi-centrifugal casting process. Molds are designed with risers at the center to supply feed metal. Metal is supplied at the center and often used on parts on which center of the casting is machined away, thus eliminating the portion where quality is lowest. So you can see here in a semi-centrifugal casting, it is vertical type. The rotation is in a vertical direction. You could see here. And here this is scope and drag. It is made up of, we can see this is the casting, and here this is the, we can say the cavity or the mold. And what we do is molten metal is poured in at the center portion, and then the mold is rotated. As the mold is rotated, due to centrifugal force, the molten metal will be thrown away from the center, and it will be filled in the outer side of the casting or outer side of the mold. So what happens? The outer side will be filled with molten metal, and once we finish it, we can cool it, and then after solidification, we get a part. Normally, a problem associated with semi-centrifugal kind of casting is center area normally will have a less strength comparing to outer area, because from the center area, due to speed, the molten metal will be thrown out. Hence, normally we remove the central area, the parts like wheels, pulleys, which they do not have a central portion. Such cases we can go for a semi-centrifugal casting process rather than going for a tubular part or a pipe, etc. So this is all about this process. Then we have furnaces for casting processes, different furnaces such as cupolas, direct fuel fired furnaces, crucible furnaces, electric furnaces, induction furnace. These are the different types of furnaces which are used to produce, or which are used to melt solid metal to molten metal. Cupola furnaces are very famous. They are used for, you can see here, we have in iron, coke, flux, and possible alloying elements is loaded through a charging door located less than half away up height of the cupola, used only for cast irons. For melting cast irons, we are using cupola furnace. Now we have metals. What are the metals which can be used for casting? Normally we go for ferrous and non-ferrous metals. So in ferrous category, if you go for cast iron, typically the pouring temperature is 1400 degree. Cast iron castings in several times that of, so one of the most commonly casted material is cast iron. And then steel, pouring temperature is 1650 degree. Attractive material with excellent mechanical properties. Complex shapes can be produced by steel. These are the commonly used ferrous metals: cast iron, which is the most widely casted material, and then steel. Whenever we talk about non-ferrous, we have aluminium, pouring temperature 660, and lightweight, very castable, very easy to machine properties of aluminium. Then when we talk about copper, we have copper alloys like bronze, brass, and aluminum, bronze, etc. Corrosion resistance, normally used for producing pipe fittings. Then zinc alloys, highly castable, good fluidity, melting temperature is normally 419 degrees Celsius. These are the general metals which are castable or which are used for casting processes. Now, one of the examples given in here, a true centrifugal casting operation to be performed horizontally to make copper tube, and outer diameter is given, inner diameter is given. So we have to use a centrifugal casting technique here, and the outer diameter of the casting is 25 centimeter. Convert it into meter. We have an equation for the casting process. The speed should be 30 over pi square root of 2g gf by d, and here you can find 30 over pi square root the gf, the g factor which we take, which is given as 65, which is a constant. And using this, what we can do, we can calculate the minimum speed required for casting, which is 68 T1.7. In here 2g by d, d is taken as outside diameter of the casting, which is 0.25. Outer diameter of the casting is equal to inner diameter of the wall of the mold, and that's why we go for 0.25. So using this equation, we can find out the minimum speed required. Another example is given here. Please go through it, and we are going to discuss this example in detail in our tutorial class. So till that time, please go through the tutorial and how to solve, please go through the solved example, how to solve it, and we will discuss it in detail in the tutorial. Thank you very much for listening, and we will proceed to module 2 in the coming week. Thank you very much.